In this video, I'll discuss some tips and bright ideas for establishing trig identities. We'll start with the definition. An identity is an algebraic statement of a quality that is true for all values of the variables for which it is defined. As an example, you might think about the square of the binomial x plus y. X plus y to the second power is equal to x squared plus 2xy plus y squared. This is not just true when x equals 2 and y equals 3, or when x equals 7 and y equals -1. It's true for any values of x and y that you can dream up. In this video, though, we'll focus on trigonometric identities. In our first example, we'll establish the identity cosecant divided by secant is equal to cotangent of theta. So this is true for all values of theta. So the plan is not to solve for theta, but instead to verify that the equality stated here is true. So I won't assume that they're equal in the process. Instead, I'll start on the left-hand side, and it's generally a good idea to start on the more complicated side. And I'll just rewrite that here. Okay. And then next, and by the way, I'm always going to work vertically. And this is something that you should practice as well, too, because working vertically, you can always catch mistakes that you might be making. Next idea I have in order to establish this identity would be to take this fraction and switch it to sines and cosines. So I'm going to use the fact that cosecant is 1 over sine theta, and secant is 1 over cosine theta. I'll make that little switch there. Okay, so now I have that the left-hand side is equal to this, 1 over sine plus 1 over cosine. And the goal here, of course, is to show that what I've really got on my hands is just cotangent. So in my next step, I'm going to take this fraction in the numerator and multiply it by the reciprocal of that fraction in the denominator. So take care of that division. And as you can see, when I do the multiplication there, I get cosine theta over sine theta, which is indeed equal to cotangent theta. And that was the goal all along. I've reached my goal, and therefore the identity has been established. In our next example, I'll establish the identity 1 minus sine squared times 1 plus tan squared is equal to 1 for all values of theta. So as with the last example, I'm going to start on the more complicated side, and that's pretty clear what the more complicated side is for this particular example. I've got 1 minus sine squared times 1 plus tan squared. All right. One of the ideas that worked out nicely in our last example was switching everything into sines and cosines. And that's definitely something that you could try in this particular example, and it would work out. Another thing that you could try is you could try just multiplying out the binomials that I have here. 1 times 1 and 1 times tan squared, 1 times negative sine squared, and so on. That would work as well. But there's another way, perhaps an even better way to solve, to establish this identity. And that's using some known identities. So I notice here that I've got 1 minus sine squared. And it's a known fact at this point in the year that for any angle theta, sine squared plus cosine squared is equal to 1. That's our standard Pythagorean identity. And as a consequence of that, you can see that 1 minus sine squared is the same as cosine squared, right? So I can replace 1 minus sine squared with cosine squared. I can actually do even better than that because 1 plus tan squared is the result that we get when we take sine squared plus cosine squared equals 1 and divide through by cosine squared, right? That's another Pythagorean identity. And so I can replace 1 plus tan squared with secant squared of theta. Okay, and at this stage, it's pretty easy to see why this expression that I've got here is going to simplify to just 1. I rewrite secant squared as 1 over cosine squared. Of course, cosine squared times its reciprocal is equal to 1. And that was the dream all along. So using known identities is a really useful tip when you're establishing new identities. In this example, I wish to establish that sine theta divided by 1 minus cosine theta is equal to cosecant plus cotangent of theta. So here I think we could probably debate which side is more complicated. The right side's a bit more complicated because it doesn't have simple sines and cosines, whereas the left side is a bit more complicated because it has this fraction. So when this is the case, you might just pick a side and get moving. So I've got cosecant of theta plus cotangent of theta, and I wish to show that this is the same as the left-hand side of the equation. So I start off by perhaps switching to sines and cosines. This gives me, instead of cosecant, 1 over sine. And instead of cotangent, I've got cosine over sine. Okay, now I've got 2 fractions, and in order to add the fractions, I need a common denominator. Luckily here, I've already got a common denominator. Both of the fractions are over sine of theta, and thus I can rewrite this way. Okay, at this stage, perhaps you start to run out of some ideas. You can see structurally 1 plus cosine theta over sine theta is very similar to the goal here, sine theta over 1 minus cosine theta. You might think, what can I do from here that might finish up the problem? There is a key trick to know, and it's one we've seen earlier in the year when we worked with radicals, and that's multiplying by what we call a well-chosen 1. In this case, a well-chosen 1 might be 1 minus cosine theta over 1 minus cosine theta. And let me show you why that is a good choice for the multiplication. In the denominator, I get sine theta times 1 minus cosine theta. But in the numerator, I get the difference of squares. 1 times 1 is 1. Outer and inner terms cancel, and cosine times cosine is cosine squared. And that's a nice result there in the numerator, because you'll see that that is our Pythagorean identity showing up again. Sine squared plus cosine squared is equal to 1, and thus 1 minus cosine squared is equal to sine squared. So now I'm rolling. I replace 1 minus cosine squared with sine squared. I've got a sine theta as a factor in my denominator. And that shows me that I am indeed able to cancel a sine in the numerator, one of the factors of sine in the numerator, with the factor of sine in the denominator, leaving me with the goal of sine theta over 1 minus cosine theta. Let's summarize those examples by listing a few of the bright ideas that were mentioned. Always work vertically. You're more likely to catch an algebraic error this way. It's a good idea to start on the more complicated side because it gives you more ideas to get yourself started. Sometimes it's a great idea to switch to sines and cosines, and that's primarily because you're more familiar with the properties of sine and cosine, though sometimes switching to sine and cosine actually will add some extra steps to the process, and it's never a problem to do 10 steps versus 5 steps in order to establish the identity. It's great to use your known identities and maybe keep a list of all of the trig identities that you already know, such as Pythagorean identities or cofunction identities or reciprocal identities. There will be more coming soon. Factoring and canceling and finding a common denominator and multiplying by a well-chosen 1, these are all algebraic skills that you want to have mastered and at the ready as you're solving identities. And then the second to last idea there, always keep an eye on your goal. After each step, look back to see where are you trying to get there and where are you trying to get and what might you need to do to get there. And last but not least, you'll see that some of these trig identities get really, really, really challenging. and it is an exercise in mathematical creativity. So don't expect the first thing that you try will always work. Sometimes you'll take a wrong turn and have to double back and try again. Take some joy in that process of trying to figure out just the right pathway that will get you there. And keep in mind that there might not be only one pathway. You might see it a little differently than someone else. Lastly, I should point out the big idea behind establishing trig identities. There are so many relationships between sine and cosine and tangent and the other trig functions that allows us to make expressions and equations in a number of different equivalent ways. By learning to establish identities, we'll be able to prove that these different representations are indeed equal.